Welcome back to the course Fluid Mechanics. We continue our discussion on the concepts by learning the fundamental properties of fluids. Fluids are substances capable of flowing, having particles which easily move and change their relative position without a separation of the mass. They offer practically no resistance to change in form. They readily conform to the shape of the solid body with which they come into contact. Fluids may be divided into liquids and gases. The principal differences between them are a liquid has a free surface and a given mass of a liquid occupies only a given volume in a container. Liquids are practically incompressible and usually may be so considered without introducing appreciable error. On the other hand, gas does not have a free surface, and a given mass occupies all portions of any container regardless of its size, and gases are compressible and usually must be so treated. Recall Newton's second law of motion stating that the force is directly proportional to the product of mass and acceleration. To be able to compute it, we introduce an equality sign with a constant k, a proportionality factor, which is made equal to 1 by two different systems of defining units. The gravitational system makes k is equal to 1 by defining the unit of mass. With the FPS system, the commonly used value for the gravitational force G is 32.2 feet per second per second. The SI or metric system commonly uses the value of 981 centimeters per second per second. The absolute system makes k is equal to 1 by defining the unit of force whereby, in the FPS system, 1 pound mass is meant an amount of matter equivalent to that in a block of metal known as the standard pound kept in Washington, D.C. The metric system uses gram as the unit of mass, which is defined as 1 of 1,000 of the mass of a block of platinum kept in Sevres and known as the kilogram prototype. Let's move on to the general properties of fluids. First is unit weight with the symbol omega. Unit weight is defined as the weight of a certain fluid per unit volume. In equation form, it would look like unit weight is equal to weight over volume, or omega is W all over V. The standard unit for this parameter is pounds per cubic foot in the FPS system and Newton per cubic meter for the metric system. Let's have an example for unit weight. So the problem states, determine the unit weight of a fluid which has a mass of 50 kilograms and volume of 0.25 cubic meters. Since what we are looking for is unit weight, then our formula is applied, but then the given is the mass of the liquid instead of its weight, so we would have to convert our equation from omega is weight over volume to mass times gravitational acceleration over volume. From physics, you have already discussed that weight is some kind of a force which requires mass and acceleration just like Newton's second law of motion. Plugging in our values, omega is equal to 50 kilograms times 9.81 meters per second squared all over 0.25 cubic meters, which would result to 1962 newtons per cubic meters. Note that the kilogram meter over square second is denoted as Newton. The next parameter is mass density, which is designated as ρ. Mass density is defined as mass per unit volume. In equation form, mass density is equal to mass over volume, or ρ is equal to W all over V. The unit for mass densities is logs per cubic foot in FPS and kilogram per cubic meter in SI units. Now let us check the relationship between mass density and unit weight. We have studied that ρ is mass over volume and omega is weight over volume. If we are going to convert weight as mass times gravity, we would notice that the resulting equation of omega is mass times gravitational pull over volume. Observe that m over v is density ρ, thus we can say that the unit weight is mass density times gravitational acceleration g. Let's work on some examples. Determine the mass density of a fluid with a unit weight of 1200 newtons per cubic meter. From the last formula we discussed, we can extract ρ as omega over g. Checking our given, which is only unit weight of 1200 newtons per cubic meter, we can compute ρ by dividing this value with 9.81 meters per square second. Note that the newtons has been expanded as kilogram meter per square second for you to see that the units basically cancel out, leaving us with kilogram per cubic meter. So the answer is 122.32 kilogram per cubic meter. The other problem states, what is the mass density of a fluid weighing 800 newtons in 0.65 cubic meter? Mass density raw has the formula m over v, where mass is converted as weight over g. Then plugging our values, 800 newtons converted to mass by dividing it by 9.81 meters per square seconds divided by 0.65 cubic meters would result to 125.46 kilogram per cubic meter. Hang on tight for our next module on specific gravity, viscosity, surface tension, and capillary action.